Welcome everybody to the AFSEM webinar, and depending from where you are joining us, good morning, good afternoon, or good evening. My name is Chris Schwalb, and me and my colleague Marcel will use the next 40 minutes to introduce to you the AFSEM microscope. We will show you how you can use it to perform real in-situ correlative analysis by combining AFM and SEM in one interactive experiment. I will start in the beginning by giving you a brief introduction of the AFSEM system, highlighting some of its unique features. After that, Marcel will show you step by step how to perform a true correlative experiment with the AFSEM. Then we will present to you the latest application measurements and close with answering your questions that will come up during the webinar. So I encourage you to use the chat window on your screen and post your questions, and we will then try to answer them at the end of the webinar. Before we start, I need to mention one thing. We will show you several videos during the webinar, and depending on the bandwidth of your internet connection, there might be a short delay between the audio and the video feed. If that happens, just stay with us. It will be resolved once we get back to the slides in the presentation. Okay, so why do we want to perform correlative analysis? Well, let's start by looking what you typically see with the SEM. There you typically see your sample in a 2D representation in a grayscale image, and if you now add the EDX capability, you can, in addition, extract also the chemical information of your sample. For this special case, you see aluminum and gold lines on a silicon substrate. If you now look at the same sample with the AFM, that is what you see. You get a beautiful 3D topography information with sub-nanometer resolution in Z, and if you're working with a conductive cantilever, you can also extract the electrical properties of your sample in the same measurement. But if you now want to correlate the AFM and the SEM information directly, you will find a big trench between the two techniques due to the following reasons. First, the transfer of the samples between the SEM and the AFM takes a lot of time. Second, finding exactly the same spot on your sample with the AFM and the SEM is either very time-consuming or, in many cases, even impossible if you want to look for very small features in the sub-micrometer range. Third, you cannot work with air-sensitive samples due to the breaking of the vacuum during the sample transfer from the SEM to the AFM. In the course of the webinar, we now want to show you how you can use the AFSEM to bridge the gap between the SEM and the AFM world. We will show you how you can perform AFM and SEM analysis in a truly correlative and interactive way. And this will enable you to get to an experiment where you can correlate all of your information concerning topography, chemical, and electrical properties in situ without the need to transfer your sample. So why do you want to combine these different analytical techniques? Well, each of these techniques has different strengths. If you look at the SEM, you have a beautiful large field of view that you can work with. You have high lateral resolution, and in most cases, the electron beam is non-destructive to your sample. If you now add a FIB, you can, in addition, modify your sample by performing, for instance, ion milling. And if you add an EDX, as you've seen before, you will also get chemical information of your sample structure. These three different techniques are already combined in state-of-the-art dual beam systems and are commercially available. The AFM, on the other hand, has a variety of complementary strengths. Here you can measure real 3D images with sub-nanometer Z resolution. You can analyze electrical and magnetic properties of your sample, and you can get information of the mechanical properties. This is the reason why you want to combine all of these techniques in one single instrument in order to exploit each of these complementary strengths interactively and in situ. So SEM, EDX, and AFM are a perfect fit, but it requires a really dedicated AFM solution for your SEM. And here you can see our solution for it, the AFSEM system. It is a very compact scanner design that fits the palm of your hand. And I just want to highlight 4 very unique features about our AFSEM system. First, we are not using the traditional optical readout for our cantilevers, but instead are working with self-sensing piezo-resistive cantilevers. Due to the all-electric readout, we can go with the AFSEM directly to the sample under the e-gun, even for very small working distances. Second, due to our dedicated scanner design, we are able to make a seamless integration of the AFSEM in almost any commercial SEM or dual beam system. This is a very important point that I want to make, because the AFSEM does not interfere with the normal SEM operation. For instance, if you can work in your SEM with very large samples, like for instance a 4-inch wafer, you can do the same in combination with the integrated AFSEM. And third, the handling of the AFSEM is extremely easy and intuitive. Even an unexperienced AFM user can get very quickly to the first correlative AFM-SEM image, as you will see later on in the webinar. And fourth, our AFSEM system is optimized for high imaging speeds in vacuum environment. For this, we optimize the cantilevers, the scanner, and the controller to be able to match the imaging speed of the SEM with our AFSEM microscope. So why do we use the self-sensing cantilevers? Well, first, let's take a look at how a conventional AFM is typically designed, shown in the schematic drawing here. Here the cantilever is scanned over the surface, and the cantilever deflection is measured by the laser beam that is reflected from the backside of the cantilever. This design is rock solid for measurements in air and gives you a great performance and stability. But if you now want to enter the high vacuum environment of an SEM, you will immediately face severe problems due to the high space constraints between the electron gun and the sample. This is why we chose to work with self-sensing cantilevers. This makes the optical detection obsolete and frees the space above the cantilever due to the all-electric readout. Therefore, this design provides a lot of benefits for the SEM user. You can work in combination with the AFSEM even for very short working distances. You can easily combine it with additional add-ons like gas injection systems, tensile stages, nanoindenters, or other add-ons. And, as mentioned before, it enables a seamless integration of the AFSEM into the highly space-limited environment of the SEM. Down below in the picture, you now see an integration example for the AFSEM inside, in this case, an FAI Quanta 600 SEM. Here, the AFSEM is mounted directly at the stage door of the instrument, which enables you to work with the sample freely below the AFSEM microscope. And now I will hand over to Marcel, and he will show you really step by step how to use the AFSEM in a true correlative experiment.
In order to give you a comprehensive overview, we will start in this webinar at the very beginning. That means exchanging a used cantilever with a new one for the next experiment. In a second step, we will mount the AFSEM to the SEM, quickly identify a region of interest with the SEM, and finally perform a high-resolution correlative AFM-SEM measurement. Before we start with the experiment, I'd like to make you familiar with the key hardware components of the AFSEM, which are integrated into the SEM for AFM measurements. First, the 3D positioning stage, which is used for coarse positioning of the cantilever in the SEM and the cantilever approach towards the sample. Second, the AFM scanner, which you can see here. Third, self-sensing cantilevers, which are placed and electrically connected to the AFSEM cantilever mount, which you see here. This design even allows AFM imaging, as Chris has already pointed out, below the electron column at really short working distances. Okay, then let's see how we can equip the AFSEM with a new self-sensing cantilever for our experiment. You will now recognize that another window pops up at your screen, which will display the video. If you prefer to see the video in full screen, you can just maximize the video using the Maximize button in the upper right corner of the window. In order to assure that everybody is able to see the video, even with lower internet bandwidth, I will wait for a short period of time before the video begins. In this video, I would like to show you how quickly and easily a cantilever can be replaced by a new one when working with the AFSEM. For those of you who are familiar with optical cantilevers, you know that exchanging optical cantilevers requires quite some dexterity and skill, and then of course time to do the laser adjustment. I'm not saying that you don't need any dexterity at all with self-sensing cantilevers. However, they make things for you much easier, and thus also the AFSEM system quite easy and intuitive to handle. In order to exchange a self-sensing cantilever, which comes bonded to this golden PCB that you see here in the video, just grab the PCB with tweezers. The PCB itself is really robust, and you don't have to worry about breaking it or the cantilever during handling. Take a new cantilever, attach it to the electrical connections on the AFSEM cantilever mount, and you're ready to begin with your experiment. Now you can say, okay, wait a minute. What about any alignment of the cantilever similar to adjusting the laser for an optical cantilever? And this actually is a very important point, and I'd like to emphasize this here because for me it is one of the most convincing and stunning properties of self-sensing cantilevers. To say it really clearly, there is no need for further adjustment or alignment because all necessary steps will be automatically performed by the AFSEM software. In the second part of the video, you will see how to mount the stage and the AFSEM scanner. The stage with its motors for 3D positioning can be mounted to the mechanical adapter in the SEM using only 4 screws. This allows for a quick and easy installation in almost any SEM. The AFSEM scanner is then fixed via a dovetail connection to the 3D positioning stage. Like that, the system is now ready for mounting to the SEM. Be aware before pumping down the SEM that, of course, the cantilever determines which AFM modes can be used and thus which sample properties can be measured. For the AFSEM, a vast variety of self-sensing cantilevers is available. These include long and soft cantilevers. They are mostly used for contact mode imaging, or short and stiff cantilevers for AC or dynamic mode imaging. For all different cantilevers, specialty tips are available, including high aspect ratio tips, conductive tips, wear-resistant diamond tips, and further magnetic tips for MFM imaging are currently under development. All experiments which you will see next are conducted with our SEM demo system, the FBI Quanta 600 ESEM, which is equipped with a field emission gun. Most importantly, it provides EDX capabilities for chemical analysis and is able to handle large samples as, for example, 4-inch wafers. If you'd like to know if the AFSEM is perfect for the characterization of your samples, please feel free to contact us and send us your samples, and we're happy to perform live demonstrations together with you on your sample directly here in Vienna, or also, if you're living further away, online via the internet. Now it is time to start our experiment in the SEM. In order to again assure that everybody is able to see the video, even with lower internet bandwidth, I will wait for a short period of time before starting the video. Now that you have already seen the complete system and we have chosen a cantilever to work with, we can mount the AFSEM to the SEM. As you can see here, the only mechanical parts needed for the AFSEM integration into the SEM are two mechanical adapters, which, in the case of the FEI Quanta 600, have this triangular shape. In every other SEM, these adapters might look a little different depending on the SEM that you use. However, regardless of the mechanical mounting system, all integrations have one thing in common. The integration is realized seamlessly, meaning that your SEM stays as it is and nothing has to be changed mechanically. All mounting points are already available in the SEM when we mount the AFSEM. Although the AFSEM does not interfere with your normal SEM operation, you can easily remove it from the vacuum chamber within minutes, and thus the original state of your SEM is restored. Once the stage is properly mounted, which is the case right now, the AFSEM scanner can be attached to the 3D positioning stage by sliding it into the dovetail connection. In order to assure a rigid connection between stage and AFSEM, the dovetail is fixed by a screw at the left side of the instrument. This allows for high-performance imaging in vacuum environment of your sample. Before pumping the system down, make sure to connect the electrical wiring to both the stage and the AFSEM scanner. If you use a large sample holder with many SEM stops, as in our case, or a large sample such as a 4-inch wafer, you can roughly position the cantilever above the area of interest. For that, you can rotate or move the SEM stage in X and Y direction freely underneath the AFSEM, as the SEM sample stage movement is decoupled from the AFSEM movement in X and Y direction. This allows you to image every sample that practically fits your SEM. The analysis of large samples is depicted now in the following split screen video. Let me pause this video here to explain what you see. On the left side of the video, you see the image of the infrared camera. You might recognize the sample holder with all different samples in the center of the image. In the background, you can see the AFSEM scanner. Between the pole piece of the electron column and the sample, you can find the self-sensing cantilever, which means that at the moment it is in the field of view of the electron beam. And exactly this can be seen in the right part of the split screen. If I start the video now, you can see that it is easily possible to move large distances and analyze different samples, which is only made possible because the cantilever tip is the lowest point of our AFSEM system in the SEM. The sample which we have decided to analyze today together with you is a silicon nitride membrane with circular holes etched into the membrane. This structure is covered by single or few multilayers of graphene, thus allowing for the analysis of suspended graphene membranes with the AFSEM inside the SEM. Once the area of interest is identified, the cantilever can be brought into the field of view of the SEM. In this case, we would like to measure the graphene membranes in the lower right corner of the sample. To make positioning even more comfortable, we can now tilt the SEM stage to gain tip view access. Thus, we can directly visualize the tip during the approach of the cantilever towards the sample surface. Here you can now see the automated calibration procedure for the X and Y sensors, which are used for closed-loop operation. Following this procedure, we start the approaching process. After finishing the approach procedure, we can now start imaging with the AFSEM. Let me just increase the image quality of the SEM that you have a nice view of the cantilever and the sample. Of course, not only the approach can be viewed with the electron beam, it is also possible to image with the SEM while the cantilever is scanned across the surface, which you can see in the left video of the split screen. The respective 3D image that we obtain with the AFM scan is shown on the right. You can now see distinct features of the sample appear both in the SEM and the AFM image. Using these features, it is easy to correlate the AFM with the SEM image. After the AFM scan is completed, the cantilever can again be removed from the field of view of the electron beam, and a high-resolution SEM image can be obtained from the analyzed data. At this point, you might ask how the AFSEM software looks like and which steps have to be taken from the AFM point of view in order to obtain a correlative image. An important thing to note here is that the software can either be operated in a highly automated mode, in the case of an unexperienced user. This means that the user only has to push the approach button and start the imaging process, and the software automatically takes care of all the settings in the background. On the other hand, an experienced user can access advanced settings and control all feedback and control parameters manually to optimize the AFM imaging process. During the approach, you can modify the imaging parameters, which you can see here, or you can control the feedback gains, which you can see in the lower tab. Once the approach is done, you can start with the AFM imaging, and the graphene membranes will appear. The topography image is shown in the left image, the amplitude error image is shown in the center, whereas the phase is shown in the right image. After finishing the AFM scan, the closed-loop operation now allows us to acquire a zoomed image of a specific area, for example, one graphene membrane. we can now further adjust the imaging parameters, increase the resolution, and then start a new scan. Now you can see nice features appear, for example, some graphene wrinkles in the topography image, and a very interesting feature which can be soon seen in the AFM error image is the drum effect, which is revealed by amplitude instabilities in the center of the membrane. Once the image acquisition is finished, the SEM and AFM data can be combined to a correlative AFM-SEM image showing a large field of view in the SEM image here on the left and detailed 3D information provided by the AFM. Besides the topographic measurement which you saw in this series of videos, our customers employ the AFSEM for many different kinds of applications which reach well beyond simple topographic imaging. In the next couple of slides, I would therefore like to give you an overview of the currently most prominent AFSEM applications. On suspended 2D materials such as graphene, the AFSEM enables our customers to analyze mechanical deformations of the membrane induced by the AFM tip which interacts with the sample. The interaction strength, which is given by the amplitude set point that you can see here, can precisely be controlled in vacuum environment. A high set point of 99%, which by the way is impossible to achieve under ambient conditions, represents a very low interaction strength which leaves the membrane almost undisturbed without any tip-induced deformations. You can see a respective cross-section here in this graph. However, if the set point is decreased, the membrane starts to deflect under the influence of the scanning tip. And you can now see, if you increase the set point again, that the membrane bends back up and finally reaches its original state again. And this results in an interaction force-dependent cross-section of the graphene membrane, which can be simultaneously studied using the SEM. Now, based on this series of measurement, we are often asked how long this analysis takes in the SEM, given the fact that the mechanical cantilever bandwidth is reduced due to higher Q factors of the cantilever in vacuum compared to air. At this point, I'd directly like to answer this question by showing you several measurements in the last video, which are presented in real time. What you can see in this video are real-time AFM images measured at different scanning rates of 1, 2, and 5 Hz, representing imaging speeds of 6, 12, and 30 microns per second respectively. Based on our background in high-speed AFM, we specifically designed the controller, the scanner, and the self-sensing cantilevers, such that high-speed imaging in vacuum is feasible. For this sample, we can thus further increase the scanning rates, reaching imaging speeds up to 300 micrometers per second or 50 Hz line rate. And this now only represents a total of 5 seconds per frame in vacuum, which you can see in the lower right AFM image which appears. Other situations where correlative imaging plays a crucial role are samples where the area of interest cannot be identified with an optical microscope, but the high resolution of the SEM is required. An example is the analysis of thin film growth on polycrystalline nickel surfaces. Once an interesting area is identified with the AFM, let's say this one here, High-resolution 3D topography information can be obtained with the AFSEM. And of course, the 3D data is also directly available. I'd like to specifically point out that the AFSEM now enables an interactive experiment in the SEM. In this case, the SEM is used as a fast screening tool, whereas the AFM provides the respective local growth information of the thin film. We can, for example, then measure this grain boundary here with the AFM. In case an experienced AFM user may wonder whether these triangular shapes, which you can see here in the AFM image, result from tip artifacts using diamond tips, I'd like to emphasize that the topography of these structures is real, which was proven by correlative SEM images. Let us now cross over from correlative imaging to real correlative analysis. This means that instead of only imaging the surface topography of materials, we will now in addition measure intrinsic properties of the sample, in this case the conductivity. As the underlying physics of electron irradiation sensitive nanogranular metals such as platinum and carbon is quite complicated, I'd like you to consider the following scenario. Assume you have deposited a material on top of a conductive gold electrode. So the gold electrode is depicted here with a golden color, and your sample that you have deposited is the black one. In the next step, you dope the material using different doping concentrations, which is denoted by the smaller squares here locally in this area. What you expect now to see is a change of conductivity in these doped regions, which was quantified by one of our customers using the AFSEM. In order to do that, they performed a conductive analysis by applying a voltage to the tip of a conductive cantilever while measuring the electric current from the tip through the sample to the grounded back electrode. The result which you get, besides the 3D topography, is a laterally high-resolution conductive map of the sample with sub-nanoampere current resolution. Another highly interesting application in fracture mechanics requires the AFSEM to be combined with a tensile stage. Samples on such a tensile stage are easily accessible with the AFSEM due to the unique cantilever mounting concept, allowing to measure the surface roughness of a material under stretching induced by the tensile stage in the SEM. Now consider a copper wire which is fixed between the brackets here of the tensile stage and stretched along its axis. The AFSEM now allows correlative SEM AFM imaging of the surface of the wire, which exhibits a significant increase in surface roughness under stretching, which can be quantified by the in-situ AFM measurement. Being able to measure the surface roughness as a function of the induced stretching, which in this case shows a linear behavior, is highly relevant in the field of fracture mechanics. And the AFSEM even allows to investigate necking effects, which are signs for plastic deformation of the material. Here you can even see that you can measure on an already broken wire in this specific region. Without discussing them in detail, I'd like to mention further applications of our customers, which might be exciting for some of you as well who work in a similar field. These include applications in the field of mechanics, such as nanoindentation, the analysis of micro nanostructures via additive and subtractive tomography, or if you analyze crystalline materials, the correlative SEM-EDX AFM analysis might be worth considering. By using the AFSEM, many of our customers are now able to perform interactive correlative analysis, which provides them with new insights into their sample's properties. The correlative and complementary AFM-SEM information helps them to advance, for example, in the field of basic science and technology, as well as improve products in industrial applications. I hope in this webinar all of you gained important insight into the variety of new possibilities which arise due to the correlative analysis capabilities of the AFSEM in an SEM. If you have your specific AFSEM application in mind, feel free to contact us anytime for in-depth discussions. We will then help and support you in the best possible way with your application. Having said this, I'd like to hand over to Chris again, who will briefly summarize this webinar.
Okay, I hope we could demonstrate you in this webinar how the AFSEM can really change the way you can analyze your samples in a true correlative and interactive way without the need to move your sample. And the main features we showed to you today are that the AFSEM really enables a seamless integration into most SEM or dual beam systems due to our dedicated scanner design. And in addition, it also enables the usage of novel self-sensing cantilevers in space-limited environments of the SEM, optimized for short working distances and for combination with additional add-ons like tensile stages, gas injection systems, or nanoindenters. The AFSEM is a very easy and intuitive tool and even allows an unexperienced user to perform interactive in-situ correlative analysis. And it allows for high imaging speeds even in high vacuum environment. And with this, we would now like to move to the question section and address the questions you posted during the webinar. So let me see what was posted. One question that was posted is, does the geometry of the AFSEM allow EBSD measurements?
EBSD is usually done at really a huge tilting angle, for example at 70 degrees. But depending on the SEM, we can insert the AFSEM in a way that it just tilts with your stage, and you can retract the scanner during the EBSD measurement, that it does not get in any conflict with the electron pole piece of your SEM. And once the EBSD measurement is done, you can just go into the field of view with the AFM cantilever again and do the correlative AFM EBSD SEM analysis at the same position where you have taken the EBSD measurement. The next question that was posted is, why is AFM considered as a non-destructive technique? Could the probe damage the sample? This pretty much depends on the user. So in principle, AFM can be considered as non-destructive as the tip-sample interaction strength or interaction force, for example in AC or dynamic mode, is really, really low. This can be different if you try or if you decide to use contact mode imaging, such, for example, for these graphene membranes which you have seen in the video. If you try to image these membranes in contact mode, you will most likely destroy them due to lateral forces which act on the membrane. But if you use AC mode, you will have no problem with destroying your sample. Okay, the next question was concerning a more detailed description of the specs of our AFSEM system, so concerning maximal scan size. Okay, maybe for this we can switch to another specification sheet. Okay, so basically what you can see here are the specifications of the AFSEM. So the maximum scan size of our scanner in closed loop is 34 microns, and in Z it is 5 microns.
Okay, then there were a bunch of questions concerning the cantilevers. One question was, how is the performance of the self-sensing cantilevers compared to optical cantilevers, and how much is the price for such a self-sensing cantilever?
Okay, so concerning the performance comparison of optical and electrical ones, here we have also a nice measurement which was reported in scientific reports. And here you see that for the larger cantilever, when you directly compare the same cantilever, optical readout is still better in performance than piezo-resistive readout. So you can see this here in the upper two, or in the upper row here. However, if you go to the small cantilevers, which we use in a standard way in the SEM, and this is shown in this line here, then you can see that actually the performance for topography imaging of the piezo-resistive cell-sensing cantilevers surpasses the performance of the optical one. Concerning the price, this depends on the amount of, or the number of cantilevers which you order, and we are happy to make a quote for you. So just write us an email and we can send you a quote for the cantilever. But just to give you a rough estimate, the cantilevers are around 75 to 80 euros for standard cantilevers.
Then there were a few questions concerning how can we combine the SEM image with the AFM image.
So the correlation has to be performed afterwards. So meaning after measuring your sample with the AFM and the SEM. Up to now, the SEM and the AFM are two independent systems, so you get the SEM image independently and the AFM image independently. This means that you can use, for example, Gwydion, which is used as a standard analysis tool for SPM analysis. You can use Gwydion to do the overlay.
Okay, and another question that popped up, is it possible to analyze non-conductive samples as polymers in order to obtain correlative SEM and AFM images of these polymers?
The first thing that you have to keep in mind, if you have a non-conducting sample in your SEM, you might charge the sample up, which might be difficult for you to measure in the SEM, but of course, yes, you can. So our customers have already performed the analysis of polymer samples, and in particular have made 3D analysis of the samples and determined the mechanical properties of the polymers in a correlative AFM nanomechanical experiment in the SEM.
Okay, another question is, would it be possible to differentiate between two materials in the same thin film, like tin particles and tin oxide particles?
This is a tough one. So, so if you have two different phases in your sample, and the two different phases, they might not show any change in topography, but they are just show an autecticum, then the thing what you might want to have a look at is the AFM phase, and the phase gives you an information of the energy dissipation of the cantilever when it taps on the surface. So the phase might give you an information that you have a different phase, let's say thin oxide one or a thin one, and you might see a difference in the phase there, although you do not see any difference in topography. So it might be possible, of course, yes, but it depends on the sample.
Okay, and then we have one last question. Can I do quantitative nanomechanical measurements with the AFSEM?
Of course you can. And you can do that by taking force volume maps or by doing point-by-point force distance curve analysis of your sample at the exact spot which you have identified with the SEM and where you like to do the nanomechanical analysis. For this, I would suggest that you use our calibrated diamond tips for the mechanical measurement.
Okay, so I think we will wrap it up here, and all the questions that we could not answer, we will definitely answer to you personally. Let me thank you all for your attention during the webinar. If you have any more questions or want to learn a little bit more about our AFSEM system, please visit our website at GETec or Nanosurf, or simply get in contact with us via email. We are more than happy to discuss all of your applications and see where you can really benefit from our AFSEM system. And we will post this video that you just saw the webinar as a video also online and send to the link, because I saw that some people had problems watching the videos. So you will be able to see all videos and the whole webinar afterwards when we send to the link. So thanks again for your attention, and we hope to get in touch with you soon.